This video is going to be on points of inflection. If the tangent line to the graph exists at a point where the concavity changes, then that point is what's called a point of inflection. Now, three types of points of inflection are shown here. Really, there's only two, but we'll really think of it as kind of three, but I'm only really concerned about going from concave up to concave down, okay? And notice that that horizontal or that tangent line right there goes through both top and bottom, right? So if there's a point that has a tangent line that goes directly through the point where we switch from concave up to concave down or concave down to concave up, if that's the case, then this is called a point of inflection. It's where concavity changes. So if we let f be a function that's continuous on an open interval and let c be a point in that interval, then the graph of f has a tangent line at point CF of c. This is a point of inflection of the graph, okay? When it changes from concave up to down or down to up. So to locate those possible points of inflections, really all you're doing is finding those points where the second derivative equals 0 or doesn't exist. This is similar to the procedure that we used to find the relative extrema, right, of f. We're just doing it on the second derivative. So instead of finding relative extrema, we're finding points of inflection. So that's the difference between the first derivative test and the second derivative test. The first derivative test is used to find relative extrema, whereas the second derivative test is used to find points of inflection, okay? So it's a point of inflection, I should say that if there is a point of inflection, it has to be a critical number of the second derivative. So either f double prime equals 0 or f double prime of c doesn't exist. So that's really important that just like relative extrema, same rule applies to points of inflection. Just because you have a critical number does not guarantee that it is a point of inflection, but if you have a point of inflection, it has to be a critical number. So we want to use this second derivative test to determine the points of inflection and discuss the concavity of the graph of x to the fourth minus 4x cubed. So first thing we have to do is differentiate twice, right? So if we differentiate twice, here's the first function. First derivative, we've got 4x cubed minus 12x squared, and then differentiate it again, we get 12x squared minus 24x. And notice that we can factor that because the whole point is to set it equal to 0, right? So if I set that equal to 0, I can see that either x equals 0 or x equals 2. Okay? Now, what we're going to do is we're going to test those intervals to determine if there are any points of inflection. So 0 and 2. This goes to negative infinity. This goes to positive infinity. So I'm going to use the point -1, I'm going to use the point 1, and I'm going to use the point 3. Now remember, we have to plug these into the second derivative, 12x times x minus 2. So if I plug in -1, 12 times -1 is -12. -1 minus 2 is -3. A negative times a negative is positive. That means we are concave up. Okay? Now at 0, 12 times 0, or not 0, at 1, sorry, because we got to use the test point, right? 12 times 1 is 12. 1 minus 2 is -1. That gives us a negative number, which means we are concave down. Okay? So this was concave up. This is concave down. Now we plug in 3. 12 times 3, 3 minus 2, it's a positive, positive. All this is positive, so once again we are concave up. So that means that since we went from concave up to concave down, 0 does represent a point of inflection. And since 2 went from concave down to concave up, it represents a point of inflection as well. Okay? So we tested them. We determined that indeed they are points of inflection. And you can see on the graph that we change from concave up to concave down. And here we change from concave down to concave up. Therefore, 2 points of inflection. Okay? Now, we know that the converse of theorem 3.a is not generally true. That is, it is possible for the second derivative to be 0 and it not be a point of inflection. This graph shows us one of the primary examples, and that's the graph of x to the fourth. Because if we take the second derivative, well, first derivative is 4x cubed. Second derivative is 12x squared. Now notice, every value, if we plug in equals 0, we're going to get x has to be 0. That's the only critical number. But no matter what point I pick and plug into x, it's always going to be positive. So this has to be concave up. This also has to be concave up. So if you don't have a change from concave up to down or from down to up, then you don't have a point of inflection. So no point of inflection here. So if you have any questions about the use of the second derivative, I keep calling it the second derivative test. It's not really the second derivative test. It is a concavity test and a point of inflection test, but the second derivative test is actually the next video. So if you have any questions about points of inflection or using the second derivative to find those points of inflections, please shoot me a reminder or ask questions in class.